We're going to talk about Euler's method, which is a method for getting an approximate solution to a first-order differential equation. We're going to start with a first-order differential equation in this standard form. dy dt is some function of t and y, and we'll have some initial condition, y of t naught equals y naught. We'll think of this as starting at some point here, t naught y naught, in the ty plane, and asking what can we say about a solution to this differential equation that starts at this point, t naught y naught. Well, if we had a direction field in this plane, we would find there's some direction that's associated with t naught y naught. The slope of this line segment here, the slope here, would be dy dt at that point, which is exactly f of t naught y naught. So if we imagine we have a solution that starts at this point, where t equals t naught, this is on our t-axis, and we imagine moving over to the right some amount. The amount we'll call delta t. This is the new point, t naught plus delta t. And we ask, where would our solution be? What would the y-coordinate be when the t-coordinate is t naught plus delta t? Well, it might be somewhere over here. We can, without knowing the exact solution, we don't know exactly where that is. But if all we know is that we start at the point t naught y naught, and at that point, the slope of the tangent line should be this value, f of t naught y naught, we can just, as a first guess here, assume that the function, the graph of the function is just a straight line segment there with that same slope. And then what will the coordinates here be? I'll call this point t1, y1, where now t1 is just t naught plus delta t. We've just moved over by an amount delta t to the right. That's this amount, delta t. And this amount here is just precisely delta t times the slope, f of t naught y naught. And the justification for that is that the actual y-coordinate at t naught plus delta t is just y of t naught plus delta y here. That's, by delta y we mean the actual change in y. That's just y of t naught plus delta t minus y of t naught. And you're all familiar with the differential approximation, which says that delta y is approximately delta t times dy dt at that base point here, t naught y naught, which is exactly what we're doing here. And that says exactly nothing more or less than what we say here. Y of t naught plus delta t is then approximately y of t naught plus this quantity, which is delta t times f of t naught y naught, the slope. In other words, we start at y naught, which is this height, and we add this quantity, that's approximately our delta y, and we get to a new point. And then what do? We keep doing the same thing, but we have to figure out what the slope here is. We move here by an amount, the same amount, delta t. We keep incrementing t by the same amount. We'll say this is t naught plus 2 delta t. We call this one here t1. We'll call this one here t2. We get a new y-coordinate and a new point. Say t2, y2. And then we just keep on like that, keep incrementing and approximating where our solution goes. We'll look at that here with an example. Again, this is should be a familiar example at this point, where we have the differential equation y prime equals minus t over y with y of 0 equals 1. We've already seen that the actual solution, which I've graphed here, to this initial value problem, y prime is minus t over y with y not equal 1, is y equals square root of 1 minus x squared. The graph is that of a quarter circle. And just, I'm sorry, that should be a t squared, because we're using t as our variable. And if you just check that by differentiation, you'll see that that's correct. let's say we didn't know what the actual solution looked like, and we just knew that we wanted to start right here and approximate with increments delta t of 0.1. Well, I'm going to make a table here. This is what I'll call n here in the first column, 0, 1, 2, 3, etc. This will be my t sub n and my y sub n. So what we see in the first line is that the point t naught y naught is the point 0, 1. That's where we start. How do we get future points? Well, I'm sorry, t1 will just be 0.1, which is t naught plus delta t. As you can see, this is t1, this is t2, we just increment t by 0.1, this is t3, we increment by another 0.1, t4, etc. To get y1, we just start with our previous y value, y naught, which is 1, this is our y naught, and we add delta t, which is 0.1, that's our delta t, times f of t naught y naught. In other words, the slope that would be in our direction field at that point, t naught y naught. That would be just the function f of 0, 1. Here's our f of ty up here, which is minus t over y. You can see that that would be 0 when t is 0 and y is 1. So when we increment the y1 stays the same as y naught. That's why this is still 1. And that means that as we go to 0.1, our first approximation says we just move horizontally here to the right. So we're already just a little bit bigger than our real solution. As we move to our second point, I'll show the computation here, y2, or just as before, t2, as I already said, is 0.2. y2 is going to be y1, which is 1. And now we're going to add to that our increment 0.1, that's our delta t, times f of t1, y1. This is going to be 1 plus 0.1 times f of t1, y1 will be minus 0.1 over 1. That's 1 minus 0.1 times 0.1, which is 1/100th. You end up with 0.99. So when we move out to 0.2, we're down just a little bit. 1/100th. Hard for me to draw that perfectly. We can compute using the same formula recursively. What will the n plus first y coordinate be? It will just be the nth y coordinate plus the increment 0.1, that's our delta t, times f of t sub n, y sub n, which in this case, that's y sub n plus 0.1 times minus t sub n over y sub n. So that's y sub n minus 0.1 times. We know that t sub n here, just because t sub n is always incremented by 1, this is just 0.1 times n, or n over 10. 0.1 times n over the previous y sub n. And you can simplify that a little more, but I'll leave it like that. Just with a quick calculator, we can compute these other values of y. Y sub 3 is 0.9698. Y sub 4 is 0.9389. Y sub 5 I computed to be 0.8963. And these are just 4-digit approximations. The next one, 0.8404. That's Y sub 6. I'm sorry, this one I wrote down incorrectly. It's 8963. That should be a 9. That should be a 6. Then 0.8404. y sub 7 is 0.7691. Y sub 8 would be 0.6781. Y sub 9, 0.5601. And y sub 10, which is the value at T10, which is 1, would be 0.3994. So if I plot those really carefully, you'll get here about 0.96 will be like that. At 4, we're 0.9389. I'll just plot them pretty quickly. 0.8404, we're up to here. At 7. At 0.8, we're at 0.6781, which is way up here. At 0.9, we're at 0.5601. There's about 0.5, and we're up to 0.5601. And at 1, we're at 0.3994. So if you just connect those dots, which I can't do very nicely right here, you would see our approximation. So if we had no idea what the real solution was, we would use this approximation and get an approximate solution to this differential equation, which went through these points. How would we get a better solution? Well, we might take a smaller increment. Instead of doing 10 increments of 0.1 each, we might do 100 increments each with delta t equal 0.01. And if you try this with a computer, you'll see that you stick much closer to the curve. Also notice that how far we are away from the curve gets a little worse and worse and worse as we move t outward. That's the general property of the solutions. You'll stay closer to the curve at the beginning, and the more you keep going, the more any error propagates. Nowadays, with a computer, you can easily do 1,000,000 increments with delta t equal 1/1,000,000th and get amazingly good approximations to first-order differential equations using Euler's method. But remember, Euler's method was, at least in some way, used by Euler, who was doing this all back in the 18th century. He didn't really have computers to use for this because there was nowhere to plug them in. So he designed it for use by hand, with hand computations. But it does make computer computations of numerical solutions to first-order differential equations very simple. And the whole world of numerical solutions to differential equations just begins with Euler's method. There are so many more things people do nowadays. It's a very important field because there are so many differential equations which we can't solve exactly, and we really want to get approximate solutions. I'll talk about one more example here before we go. This one's a little more complicated. Here we have y prime equals y times 3 minus ty. So this is a slightly more complicated f of t and y. We're going to start with y of 0 equals 0.5, so that our point t naught y naught is the point 0, comma 0.5. And again, we can make a table. I show you here exactly what the exact solution is. Found this with a computer. This is one that's not going to be too easy to solve, but it is something that is in principle solvable. And here's the solution. You can check that if you want. It's a lot of fun. And if you graph that, you see here, we're starting at the point 0.5. And as we go all the way to 2, we get a curve that looks like this. I'm only going to go up to 1.5, and I'm going to use pretty big increments here of 0.25. In other words, we're going to start here at t naught equals 0. We'll have t1, t2, t3, t4, t5, and t6 here, and we'll just plot our way along. So I plotted it here. Again, this is going to be n, this is going to be t sub n, and this is going to be y sub n. So t naught y naught is 0.5. t1 y1, well, t1 will be 0.25. Again, we're using delta t is 0.25. I computed, just using a quick computer here, that t1 is up at 242ch2sec7EulersMethod. T2 is 1.483. T3, I got 2.32. T4, 3.051. T5, I got 3.012. And T6, I got 2.436. And if we plot them, at least on the scale I've shown here, it's very hard to distinguish between the actual point and the curve here. It just happens even using a big increment, a relatively big compared even to the last one, increment of 0.25, we're very close to the curve at 0.5. We're up here at 1.483, right around here. When t is 0.75, we're way up here at 2.32, which is somewhere around here. At 1.0, we're right up at 3, a little over that, 3.05. And then we move over here to 3.012, just down the tiniest bit, and 2.432 at 1.5. So you can see what our approximate solution would look like. It would be very close at first. It would go up. It would show the general behavior here. And again, if we use a smaller increment and more computations, we would be able to get a more accurate picture of what the solution looks like.